Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about evaluating and graphing sine and cosine functions. Right, so one of the things you need to understand before we get into graphing sine and cosine functions is something that's called a reference angle. Now, we're going to use a reference angle to determine trig values in a unit circle based on basic values in the first quadrant. So in a unit circle, the values of the angles formed by the x-axis and the terminal ray of an angle that measure 50 degrees and 130 degrees are equal. So the 50-degree angle is an acute angle. It's an angle whose measure is less than 90 degrees, and it's in the first quadrant. So we're going to call that our reference angle. The reference angle has the same trig value as, we'll say, its other sister angles. For example, the measure of 130 degrees. The only difference might be one of sine, S-I-G-N, so positive or minus. All right, so using your calculators, go ahead and find the sine cosine tangent of 50 degrees and 130 degrees, and then ask yourself, are they the same? Are sine of 50, sine of 130, cosine of 50, and cosine of 130 the same, and why? Or are they different? So what you should find out is that the sine of 50 and the sine of 130 are the same. The cosine of 50 and the cosine of 130 are the same in value but different in sign. So when you evaluate using a reference angle, you could take a look at the value for 50 degrees and then apply a negative sign to it to come up with a value for 130 degrees. All right, so taking a look again at our example of a 50-degree angle, I could also use 50 degrees as the reference angle for 230 degrees. And essentially what you want to do as a reference angle is find the difference between the x-axis and the angle measure between the x-axis and the terminal ray. So in this case, the measure of angle R as a reference angle would be 50 degrees. The measure of angle R itself is 230 degrees, but the difference, or the angle measure between the x-axis and the terminal ray, is 50 degrees. So 50 degrees is going to be your reference angle. So in the case of finding cosine for 230 degrees, we realize it's in the third quadrant. So the value, or the sign S-I-G-N, is going to be negative. If it were sine of 50 degrees, the same thing would occur. It would be sine of 230 degrees. It'd be sine of 50 degrees, and then you would apply the negative sign to that value. All right. So you can also use a formula, either 180 plus the 50 degrees to come up with the angle of 230, or 360 degrees minus 50 degrees to come up with the angle measure in question that's part of the sister or family of angles that have a reference angle is 50 degrees. So 50, and then 130, 230, and then 310 degrees. Those are all angles with the same absolute value measure for sine, cosine, and tangent, just different in sign, S-I-G-N. So now I want you to go ahead and take a moment to fill out these values, and then we'll come back in and I'll show you the answers. So what you're going to do is you're going to find the appropriate reference angles for the angles that are in question. And then I want you to determine whether it's the same sign as the reference angle or not the same sign. And then just as a matter of discussion, the reason why we want to understand the values of reference angles is that it makes it much easier for you to find specific angle measures that are not acute very quickly. And you'll see that as we move on to evaluating other trig functions and problems in the unit circle more specifically in later chapters. So go ahead and take a moment, come back, and then take a look at your answers. Right, here are the answers for the problems. So sine of 310, and I'm not going to go through these, but just to evaluate a couple, sine of 310 degrees would use a reference angle of 50 degrees, and you're going to change the sign from positive to minus. Cosine 310 degrees would be a positive cosine 50. Cosine negative 53 degrees would be positive cosine 53 degrees. sine 1000 degrees would be a negative sine 80 degrees. Right, so another thing that we need to talk about when we're considering angle measures and trig functions are the special values or special families of right triangles. And the first is the 30, 60, 90 triangle. And then we'll talk in just a second about 45, 45, 90 triangles. So 30, 60, 90 triangles have a particular setup. And the setup is that the side opposite the 30 degree angle is going to be x. The side opposite the 60 degree angle is going to be x root 3. And the side opposite the right angle, so the hypotenuse, is going to be 2x. So if I were to relate this in terms of a length for the opposite side of 30, it would be 1. Length opposite 60 would be root 3. And the length opposite the right angle or the hypotenuse would be 2. In a unit circle, then, sine is going to end up being, sine of 30 degrees will end up being 1/2. Cosine and cosine will end up being root 3 over 2. Right, if I take a look at a 60 degree angle and apply the same relationships for the opposite sides, side opposite 30 is 1, side opposite 90 degree is 2, the hypotenuse is 2, the side opposite 60 degrees is root 3. Now, sine becomes root 3 over 2 and cosine becomes 1/2. So we've just switched the values for sine and cosine going between 30 and 60 degrees. So sine is 1 over 2. Sine of 30 degrees is 1 over 2. Cosine of 30 degrees is root 3 over 2. And then sine of 60 degrees is root 3 over 2. Cosine of 60 degrees is now 1 over 2. So one of the ways that this makes sense is, at least to me, is root 3 over 2 is approximately 0.67 approximately 0.67. And so 1/2 is less than that amount. So I know the side opposite 30 degrees is going to be shorter than the side opposite the 60 degree angle. So I can say that the longer side, root 3 over 2, applies, or the trig function where we're applying the opposite side for root 3 is going to be a larger value than the trig function for using the side opposite the 30 degree angle. Right, so the special family of right triangles, 45, 45, 90 triangles. Of course, the side opposite 45 and 45 degrees are going to be the same. I'm going to label those as 1. And the characteristic is that the side opposite 45 will be x, the side opposite 45 will be x, and then the side opposite the right angle, the hypotenuse, will be x root 2. So in this case, we have x root 2, or with your side lengths of 1, your hypotenuse ends up being root 2. So for sine of 45 and cosine of 45, they're the same value. It's 1 over root 2, which we need to rationalize into root 2 over 2. Right, so now I want you to provide the exact value in simplest form for the following trig functions using the degrees or the radians as identified. And try not to use your calculator. We'll come back in just a second, so you can pause here. And by the way, I apologize that root 3 over 2 is approximately 0.87, not 0.67. Okay, so here are the values for the different trig functions for the given degrees. All right, so now we're going to graph sine and cosine in color, and then we're going to graph 2 sine x and sine 2x. I'm going to take a look at what those look like, and I'm just going to show those to you. You can pause here to try to map those out on your own. So if I take a look at the sine function using degrees instead of radians, just for one cycle starting at 0 degrees and going through 360 degrees, I end up with 0. Sine is 0 at sine of 0. It goes to 1 sine of 90 degrees, then back down. Sine of 180 is 0. Sine of 270 is -1. And then sine of 360 is 0 again. So this is the basic look of a sine function. And so if I evaluate that in terms of the x value as radians instead of as degrees, I end up with this graph, similar looking graph, but again, the x-axis values have changed. Now I take a look at the cosine functions in degrees. Cosine of 0 degrees is 1, cosine of 90 is 0, cosine of 180 is negative 1, cosine of 270 is 0, cosine of 360 is 1. In radians, of course, pi halves, pi, 3 pi halves, and 2 pi. And then when I compare the two functions, you can see that the sine and cosine graphs are very similar in function. They have the same period, same amplitude. And so ultimately what we will end up doing is calling both sine graphs and cosine graphs as just sine graphs, because you could shift either graph either to the right or left to make the sine graph the cosine graph, or the cosine graph the sine graph ultimately. All right, and if we take a look at the different values for 2 sine x and sine of 2x, we place that in reference to the parent function sine of x. We see that 2 sine x changes the amplitude, increases it by 2. So now the period stays the same. I still go through one cycle in 360 degrees, but now my highest and lowest value become 2 and negative 2 respectively. So my period changes from 1 to 2. So on the outside here, the amplitude is changed when you multiply the graph or the sine function by a particular value. And then when the scale factor is placed inside of the parentheses in front of sine, now we're changing the period, and the amplitude now stays the same. So in the first case, amplitude changed, period stays the same. In the second case, the amplitude stays the same, but the period now is cut by a factor of 2, or is now 1/2 of what it was previously at 360 degrees. So the period is now 180 degrees. Okay, so that's it for chapter 7.4, evaluating and graphing sine and cosine functions. Hope to see you next time in the next edition of Autumn Math.